All right, so we're going to work this problem. Our strategy we talked about before was, if we can, we want to try to find all the reactions first. And then we're going to work our way through this system joint by joint. Turn the light on. So let's see if we can do that first. Can we find all the reactions in this truss? I think we can. So I'm going to draw a free body diagram over here, kind of this system. Not exactly. And I do have at B, I have an applied force of 60 kilonewtons. And then I'm going to replace my pin here at A with two forces. I'm going to call AX, AY, and AX. And then I've got a roller here at C. And we know that a roller just has one reaction, vertical. And I'll assume it's also up CY. And that's it. So I think I can find those three reactions because I can write three equations of equilibrium from my two-dimensional system. So let's do that to start with. So where should we start? Should I sum moments at B? That's a terrible place to start, right? Because I'd write one equation and three unknowns. And that's not good. Could I sum moments at C?
Good.
I could. What could I solve for if I sum moments at C? I could find AY. That's reasonable. Or could I sum moments at A?
Mm-hmm.
Yeah. So just as a tradition, I'm going to sum moments at the pin, which would be A. So I'm going to come over here and I'm going to do that. So I'm going to assume right-hand rule, and we're going to sum moments at A and set it equal to 0. So there's my equilibrium statement. So let's do that. Summing moments at A, CY creates what kind of moment about A? Positive or negative? Positive. So the force is CY, and what's the distance? This is 5 meters. And then I have the applied force, 60 kilonewtons, about A, positive or negative moment? Negative. So that's a force of 60 kilonewtons, and the distance from A to C is 10. That's pretty easy to solve for. CY is going to be 120. And it came out positive. So I did assume the right direction for CY. Now, does it make sense that CY would be up? So think about my system right here pivoting at A. If I'm pushing it down here, I better push up here. And since I have a shorter moment arm, I would expect the reaction to be larger than the force. And that all seems reasonable. Now what can I do? Well, I can either sum forces in the X or sum forces in the Y. I'll sum forces in the Y first. So there's my statement. And when I do that, what do I get? Well, I have A acting up. That's positive in my sign convention. C is up, also positive. And then the 60 is down, so that's negative. And we know CY right there. We can plug it right in there. And what do we get? AY is negative 60. Now, does that make sense? I think it does. If you think of C kind of as a pin, this kind of looks like a seesaw. And if you pull down here, you better pull down here. And since the distances are about the same, you'd expect the result to be about the same. So that seems reasonable so far. And then we're left with the last one. I'll go ahead and put it down here at the bottom. We'll sum forces in the X direction. Make sure in equilibrium. So there's our statement. And what are the forces in the X direction? AX is it. And it's positive to the right. But it doesn't really matter because that's a pretty simple one to solve. AX is 0. So I've got my reactions. So now with method of joints, we're going to pick a joint, A, B, or C, and we're going to write two equations of equilibrium. Could we do it at A? Yeah, there's two unknowns. There's AB and AC. Could we do it at B? Sure. Again, two bar forces. Could we do it at C? Sure. So we can go anywhere we want. So now, if we can do that, which joint is going to offer us the least resistance in solving for the two unknowns? How about B? Oh, think about it. If I use my traditional X and Y system, this force has X and Y components, and this force has X and Y components. So you'll have two equations in two unknowns. You can solve that, but that's going to cost you some time, right? What's the difference if I go to A? Well, AB still has two components, but what does AC have? One. So I should be able to solve for AC first, one equation, one unknown, and then use it to solve for AB. So I'm going to start. Oh, I could also apply that same strategy to C. So either A or C would be a good place to start. And just for alphabetical reasons, I'll go to joint A. So again, I'll draw my point A. Now, what did I find AY to be? AY came out to be negative 60. So that's actually down. And what did I find AX to be? 0. So I don't have to worry about it. Now I'm going to assume tension in force AC and tension in force AB. I need some geometry for this one. So what's the orientation of this element? Let's see. In the x direction it goes, what, 10 meters, and then it goes up 5 meters. So that's really like a 2-to-1 slope, right? So I'll just mark that on there to help me remember that, 2-to-1. If this were a 2-to-1 right triangle, what would the hypotenuse be? Square root of 5, right? 1 squared plus 2 squared. That should be 5, right? Square root of 5. So I like to do it that way. That way I don't have to get out my calculator for sine and cosine. So if I want the x component of AB, it's going to be 2 to the square root of 5. And if I want the vertical component of AB, it's going to be 1 over the square root of 5. So now I'm ready to go. So should I sum forces in the x direction first or the y direction first? Why? Because only one component has a y value. So I'll start there. So I'm going to sum forces in the y direction and set it equal to 0. So there's my statement. So let's do that. So in the y direction, I have the vertical component of AB, which is 1 to the square root of 5. FAB, acting up, positive, and then I have the 60 kilonewtons acting down. So I should be able to solve for the force in AB, whatever 60 times the square root of 5 is. Anybody got that? 136, I'm guessing. 134. Oh, 134. Is it exactly 134?
116.
Oh, that's close enough. I'll put a 0.2 there, 1.6. Now, I don't really care. If you're working this for me on the exam, 134 something will be fine. Pay attention to Mastering Engineering. I think they're real sticklers about significant figures. So make sure you read the question carefully. I want to say 3 significant figures is what they like, unless they tell you otherwise. So just keep that in mind. Hey, it came out positive. What does that mean? Tension. Does it make sense that AB is in tension? Well, how is this point B going to move under this load? Is it going to move up? No, it's going to probably move down. Is it going to move to the right or to the left? Probably slightly to the right. So that means that this point AB is going to, the length AB is going to get a tad longer. If it gets longer, it must be in tension. While we're there, can we get something else now? Well, I can solve for AC, right? How do I do that? Well, I'll come back and work the problem by summing forces in the x direction. So looking at the x direction, what do I have? I have my force AC, which is positive, to the right. And I have the x component of AB, which I just solved for. It's also to the right, so it's positive. And the x component would be 2 over the square root of 5 force AB. Now remember, I already know AB, so I can just plug it right in there. So I'm plugging in a positive value, so this term is positive. AC is positive, so when I solve for AC, what should I get? Negative. So what is that value? I want to say it's going to be 120? That seems 120?
119.8.
Yeah, 120. And it's negative. Now, does it make sense that AC would be negative? I think so. When you push this thing down, C is more likely to move to the left. And that means AC would contract, get smaller, so it would be in compression. So really, the only thing we have left here is what? BC. And do you want to get that by going to B or C?
C.
Here I think the clear choice is C. Because the geometry here at B is going to be painful. When you go here at C, well, we already know one of our components is just in the x direction. And then this one has x and y. I should be able to come here and sum forces just in the y and get that solution. So let's go to joint C. So there's my free body diagram for C. Now what do I know at C? I solved for CY, and it was 120, and it was acting up. So there's my 120 kilonewtons acting up. And of course I have my force in AC, and I have this other force I don't know, which is in BC. And looking at the geometry of the line between C and B, I go over 5 and up 5. That's basically 1 to 1. And then we know the hypotenuse is square root of 2. So, just to remind you, I already have AC, right? We found that. So I'm just looking for what's the quickest way to get BC. I could sum forces in the x and get it. I could sum forces in the y and get it. But if I sum forces just in the y direction and get my solution, I will not include AC. And if AC were incorrect, then that would affect my answer. This way it won't be. So I'm going to sum forces in the y direction and make sure that's in equilibrium. And what do I get? Well, I'll need the y component here, which is acting up. So that's 1 over the square root of 2 FBC acting up. And 120 is also acting up. So I can solve for FBC. It looks like FBC is going to be negative. I don't know what it's going to be. 50 something? 70 something?
170.
Oh, 170. Sorry. Exactly 170? Pretty close? 169.7. I'll just do that. And that'll be kilonewtons. So just to finish our review, does it make sense that BC is in compression? Well, yeah, as this point B kind of comes down and C moves just a little bit, you can see that BC will probably get shorter, and it makes sense that it was in compression. Any questions about that one? It's a pretty simple one to get started. All right.